Hi, welcome back to another video. In this video, we will talk about oscillator. And in order to understand oscillator and do the simulation of an oscillator, in this case, I choose the Wien-Bridge Oscillator. We need to go through the concept of the feedback system, the loop gain, its contribution to oscillation inside the feedback system, and finally, how to calculate the frequency and oscillation. First, let's go to the feedback system. So, what does it mean, feedback system? Feedback system means we not only consider the input go through a system and then obtain the output, we also use part of the output go to another system, and thus part of the signal will contribute to the input branch and go to the output again. As a result, we have a feedback because we use also the output signal to go to the output signal again to a feedback system. As a result, we have the feedback system, but we have two types of feedback system. One type is positive and the other type is negative. Why we call a type is positive? Because when we take the output, we go to the feedback system, and here its contribution is add to the input signal. Because of the addition, the feedback is called positive. Go to the negative. It will take the output, go to a feedback system, and we subtract that signal with our input signal. Because of the subtraction, we call the feedback negative. After we understand the image or the concept of the block diagram representing a positive feedback and the negative feedback, we need to define the transfer function of the block diagram. And when we talk about the transfer function of the block diagram, we consider the output signal over the input signal. And in order to obtain that, let's look through, for example, the positive feedback here. First, we consider the input signal. Please pay attention to the arrow direction. They are very important when you're deriving the transfer function of an abstract block diagram of a circuit. Again, input signal go with this direction of the arrow. We'll have the plus sign. That's why we have plus x, and the plus x go through the system A to the output y. As a result, we have plus x times A. And for the feedback branch, the input is from the output y. The output y times the feedback system B, and that signal will have the plus sign. So we have the plus sign here, and plus y times b again go through the system A, so we have plus y times b times a to the output. As a result, we obtain this equation, and from that equation, doing some mathematical transformation, we obtain the ratio between the output y signal over the input x signal and obtain the formula here. Similarly, we can obtain the transfer function of the negative feedback system. Now let's go to some definition. We call this formula as a closed loop gain. Why is it closed? When you look at this block diagram, everything is closed as a loop. So this loop is totally closed. We call it closed loop gain. When we don't consider the feedback branch, we don't consider this branch, only the input signal go through the system A to the output signal Y. We have an open direction. As a result, the system A is named forward gain, or sometimes it can be called open loop gain. Next is the feedback gain, because it's on the feedback branch, so they name the B system as feedback gain. Finally, they define the multiplication between A and B as loop gain. So all of the definitions relating to the feedback are defined. Let's go to the main focus to the oscillation, which is the loop gain. So they introduce the Barkhausen criterion. With the Barkhausen criterion, if the loop gain B, in order to understand the magnitude and the phase shift of a loop gain of a system, if you don't understand, please read the book in the reference in the comment section of this video, or you can search for the signal system book. It explained very thoroughly the definition of the magnitude and the phase shift of a system. Let's assume that you all know about the magnitude and phase shift of a loop gain of a system AB. So let's assume so. Now let's talk about the Barkhausen criterion again. It has two conditions. The first condition is that if the loop gain B has magnitude 1 and the phase shift of the AB in the positive feedback is 0 or 0 plus the integer times 360 degrees, our positive feedback will have an oscillation. Why? So let's say again, if the loop gain B has a magnitude 1 and phase shift is 0, then AB system transfer function actually is a real number 1. Is actually 1. So 1 minus 1 is 0. So the denominator is 0. Why? The numerator is a system, is a defined system. So a defined system over 0 will make the whole system to be unstable. Because the whole system is unstable, it will cause an oscillation at the output. Similarly, if we have a negative feedback, our loop gain has magnitude 1 and the phase shift when the negative inside the negative feedback, the loop gain has the phase shift 180 degrees. Literally, the loop gain is minus 1. If we look at the transfer function of the negative feedback here, 1 plus minus 1 is 0. Again, the system will be unstable and creates an oscillation at the output of the system. That's why loop gain is very important. If the loop gain satisfies the Barkhausen criterion, depends on the system, either positive or negative, it will make the system to be unstable. Because of the instability of the feedback, an oscillation will be introduced at the output. And let's go to an example. So the Wien-Bridge Oscillator, this one is only part of the Wien-Bridge Oscillator, but is very important. It's like the heart of the Wien-Bridge Oscillator, which decide the frequency of the oscillation at the output. When we look at the system, a circuit, electronic circuit, we need to define the transfer function between the output and the input. Again, if you don't understand what does it mean the transfer function of a circuit or a network, please refer to the book in the reference comment section. The book covers very well the topic, and also signal system book will give you the good definition of the transfer function of a circuit. So according to the theory of the network, or theory of a circuit, we can obtain the transfer function of the output and the input. Let's assume that this is a part of our AB system. So if it's a part of the loop gain, and the loop gain, in order to obtain the oscillation, the loop gain must be real number. The loop gain must be real number. And if this part deciding the loop gain, and the loop gain is real number, we need to eliminate this imaginary part. And in order to eliminate this imaginary part, we will have this condition. And because this condition, we can obtain the frequency, or the angular frequency. This is the frequency, and this is the angular frequency of the oscillation. In case we have the resistor, the resistor with the same value, and also capacitor to 2 capacitor with the same value, we can calculate the frequency at the oscillation of the output. In this case, I choose 1 kilo ohm for each resistor and 0.159 microfarad for each capacitor. According to this condition, the resistor here is 1 kilo ohm and the capacitor here is 0.159 microfarad. We obtain the frequency approximately 1000 Hertz. And in case that this transfer function is a real number, it has the value 1/3. So if we use this condition and we eliminate the imaginary part, our transfer function will be a real number, which is 1/3. However, this is only one part of the loop gain, because the loop gain must have the magnitude of 1. And in order to make this one have the magnitude of 1, we need only amplify the signal with 3. And because the number is already real, so if it's already real, then the phase shift of the loop gain can, let's say, can be 0. If it's 0, then we just need a positive feedback. So what does it mean? In order to obtain the oscillation, we need to satisfy the Pearson criterion. And in order to do that, we need to amplify the signal by 3. And our signal is already real number, positive real number with a phase shift 0. So we need a positive feedback. So we need an amplification with positive feedback of 3. As a result, this is the final circuit of the Wien-Bridge Oscillator. Here you could see that we use the feedback positive, and with the positive or the non-inverting amplifier with such a configuration, we could obtain the 3 amplifications. As a result, our loop gain AB will be equal to 1 in the positive feedback. And again, according to the Pearson criterion, in the positive feedback, if the loop gain is equal to 1, definitely at the output we will have an oscillation. So this is the first part of the oscillator, where I introduce only the theory. In the second part, I will do the simulation in LTSpice. So please wait for the second part, and see you again. Goodbye. If you find that the video is helpful, give me a like or subscribe. Or if you find something wrong, just leave me a comment. I will answer whenever I could. And see you. Goodbye.